Welcome to our exploration of the biomechanics of human bone. In this video, we'll uncover how the unique composition and structure of bone allow it to withstand the many mechanical loads our bodies face every day. From supporting our weight to enabling movement, bones play a crucial role in our daily lives. We'll dive into the mechanical functions of bone, its composition, and how factors like aging and bone porosity affect its strength. Whether you're a student, a health enthusiast, or just curious about how your body works, this journey will give you a deeper appreciation for the remarkable engineering behind human bones. Bones serve as the rigid framework of our bodies, providing essential support and protection for vital organs and tissues, but their role goes beyond just being a protective shell. Bones also form a system of levers that muscles use to create movement. Imagine your bones as sturdy beams and your muscles as the force that moves them. This lever system is what allows us to walk, run, jump, and perform countless other activities. The ability of bones to act as levers is fundamental to human movement and is a testament to their incredible design. Lever in biomechanical terms is a relatively rigid object that can rotate around an axis when a force is applied. In our bodies, bones act as these levers and joints serve as the axes. When muscles contract, they apply force to bones, causing movement. This system is efficient and allows us to perform complex tasks with precision and strength. The interplay between bones and muscles is what makes human movement so versatile and powerful. One of the key properties of bone is stiffness. Stiffness refers to how much a material resists deformation when a force is applied. In bones, stiffness is measured as the ratio of stress to strain, essentially, how much force is needed to change the shape of the bone. This property is crucial because it determines how well bones can support our bodies without bending or breaking under pressure. Another important property of bone is compressive strength. This is the bone's ability to resist forces that press or squeeze it together. Compressive strength is what keeps our bones from collapsing under our own body weight or during activities like jumping and running. It's the maximum load a bone can handle before it deforms or breaks, making it a vital aspect of bone health and function. Stiffness and compressive strength of bones are largely due to the presence of calcium carbonate and calcium phosphate. These minerals form the hard, dense part of bone tissue, giving bones their rigidity and ability to withstand heavy loads. Without these components, our bones would be much weaker and more prone to injury. While minerals give bones their strength, collagen is responsible for their flexibility and tensile strength. Collagen fibers allow bones to bend slightly without breaking, which is essential for absorbing impacts and preventing fractures. This balance between rigidity and flexibility is what makes bones so effective at protecting our bodies and supporting movement. As we age, our bones gradually lose collagen, making them more brittle and prone to fractures. This is why older adults are at a higher risk of bone injuries. Maintaining bone health through proper nutrition and exercise can help slow down this process and keep bones strong for longer. Water makes up about 25 to 30% of bone weight and plays a significant role in bone strength. The water content helps maintain the flexibility and resilience of bone tissue, allowing it to absorb shocks and recover from stress. Proper hydration is thus essential for maintaining healthy bones. Bone tissue can be categorized based on its porosity. Cortical bone is dense and compact with low porosity, found mainly in the shafts of long bones. In contrast, trabecular or cancellous bone is less compact and has high porosity, located at the ends of long bones and in the vertebrae. These differences in structure affect how each type of bone responds to mechanical loads. At the microscopic level, bones are organized into structures called osteons, which contain central Haversian canals. These canals allow for the passage of blood vessels and nerves, ensuring that bone tissue remains healthy and well-nourished. The arrangement of osteons contributes to the strength and durability of cortical bone. Cortical bone is much stiffer than trabecular bone, allowing it to withstand greater stress but less strain. This means it can handle heavy loads without bending much. On the other hand, trabecular bone is spongier and can absorb more strain before fracturing, making it ideal for areas of the skeleton that experience varying forces, such as the ends of long bones and the vertebrae. Bones are anisotropic, meaning their strength and stiffness vary depending on the direction of the applied force. This property allows bones to adapt to the different types of loads they encounter, such as compression, tension, and shear. The anisotropic nature of bone is a key factor in its ability to support and protect the body efficiently. Bones are strongest when resisting compressive forces, such as those experienced when standing or jumping. However, they are weakest when subjected to shear forces, which can cause sliding or twisting. Understanding these differences helps explain why certain types of fractures are more common in specific situations. Summary: the human bone is a marvel of natural engineering. Its unique composition and structure allow it to provide support, protect vital organs, and enable movement. The balance between stiffness, strength, and flexibility ensures that bones can handle the diverse mechanical loads we encounter every day. By understanding the biomechanics of bone, we gain valuable insights into how to maintain bone health and prevent injuries throughout life.